Section 2.2, Vectors in 3 dimensions. We just finished working with plane vectors, that's 2-dimensional vectors. Now we're going to step it up by making 3-dimensional vectors. Most of life happens in 3 dimensions, so being able to describe things mathematically that are in 3 dimensions is very useful. Vectors is the simplest way for us to be able to do that, so let's take a look at some 3D vectors. In order to talk about 3 dimensions mathematically, we need to be able to visualize them graphically and talk about them with some kind of convention. So first, let's talk about a 3D coordinate system. We're used to the Cartesian plane, the XY plane, but that's only 2 dimensions. So if we throw a third axis on that, we can create 3 dimensions. We'll have an x-axis, a y-axis, as well as a z-axis. We'll refer to this as R3, or 3D. In this class, we're going to stick with using the right-hand rule, which tells us how these axes are positioned relative to each other. The index finger is along the positive x-axis, the middle finger is along the positive y-axis, and the thumb is along the positive z-axis. And if you hold your hand out where all 3 of those fingers, yeah, I am calling the thumb a finger, that's right, where all 3 of those fingers are perpendicular to each other, kind of like how you see in the picture, you can imagine how that creates a 3D coordinate system. All 3 axes are perpendicular to each other. We call this orthogonal. All 3 of these arrows, the red, blue, green, they're all perpendicular to each other. Now it is possible to use a left-hand rule, so if you're left-handed, don't feel left out. However, it changes the way we would describe things. For example, my research was in fluid dynamics, and we talked about the depth of the ocean for some of our applications. Well, when you talk about depth, you use a positive number to represent how deep something is, rather than using a negative number to show that it's below a sea level. So we used the left-hand rule, which flipped the z-axis to point in the opposite direction of the right-hand rule. So it is useful, but let's stick with just the right-hand rule for now. That way we can all be sure that we're on the same page. Knowing the right-hand rule is very useful because in 3 dimensions, you can look at an object from different perspectives. And so if you're able to change your perspective simply by rotating your hand to look at it from the back or from the front, from the bottom or the top, you can help gain your bearings about which axis should be pointing in which direction. Now that we know how the axes are related to each other, let's look at some graphs. We're going to play in GeoGebra with a plot of a point, and we're going to look at how the coordinate planes exist in this new 3D system, and we're going to replace our old idea of quadrants from 2-dimensional graphs with a new idea of octants. On the screen, I have my GeoGebra 3D calculator open, and I have a few things already typed in the calculation field. I put those in so that we can save time here, but I'm going to walk you through what each of them are. First off, the point A I have described here by the coordinates A, B, C. We have 3 coordinates inside of this point, so we call these an ordered triple. These ordered triples are going to help us place points in 3 space relative to the origin. So for example, if I let A be 0, and if I let B also be 0, and C be 0, then my point is sitting right at the origin. It's at the point where all 3 of our axes meet up. If we're not sure which axis is which, let's notice that this is the pointed direction, so that's positive. This is a pointed, that's positive. This is pointed, that's positive. So we can use our right-hand rule to figure out if we have X, Y, and Z in which order. So if red is the X-axis, then green would have to be the Y-axis, and blue would have to be the z-axis. And right now I have my labels turned off, but I can go ahead and turn them on. They're a bit hard to see, but they are there, so maybe that's helpful, maybe not. Okay, let's play with our sliders here. A, B, C. These I'm calling sliders because they have this little slider function to them where I can change the value of A, and anywhere else that I have it typed in, it will also update as I'm changing the value of A. So if I wanted to allow that slider to play, I can see that changing the value in the first position of our point is allowing that point to slide along the x-axis. If I'm using a positive number in that first coordinate, then I'm on the positive side of the x-axis, and if I use a negative number, then I move back to the negative side of the x-axis. Pretty intuitive, I hope. Similarly, I can allow the b value, that is the second part in our ordered triple. I can let that move. Positive is going to take us to the positive y-axis. Negative is going to take us to the negative y-axis. And if we want to speed this up, we can simply by clicking on these fast forward arrows. Or if I want to slow it down, I can slow it down by clicking those as well. Lastly, we might want to see how things change when we allow the third part of this ordered triple to vary. Positive is going to take us up to the positive z-axis. Negative is going to take us down to the negative z-axis. And so we can see that each one of these values is related to one of the axes in our 3D coordinate system. If I'd like to plot a point that's not at the origin, then maybe I'll pick some value for x and some other value for y, and then some value for z. So I allowed this point to move parallel to each of our axes to get to where we are. All three of the values that I have in my ordered triple are positive. So notice that I'm in the portion of the coordinate system that has all three positive axes pointing where I'm at. Often textbooks will refer to this as the first of 8 octants, so octant 1. And then they'll say the rest of the octants, we don't have names for them. But I like to name them so that we can refer to each one of them and more quickly find out where to go. So having all three positive puts us in octant 1. If I were to let the x become negative, I like to call that octant 2. So if x is negative, but y and z are positive, I like to call that octant 2. If I keep x negative and let y become negative, I like to call that octant 3. If I switch my x to now become positive again, I like to call that octant 4. And that's the first 4 octants. Notice that they were all above the x and the y axis. And I rotated in the same orientation that we used to rotate for the quadrants. So the top 4 octants, I like to name them conventionally the same way that we did the 4 quadrants that we had in 2D. But we haven't talked about 4 other parts of 3D, and that's when we have all of these 4 combos, but with z being negative. So if I go back to letting x be positive and y be positive, but I force z to be negative, now I'm below the xy plane, I like to call that octant 5. And if I let x become negative, I like to call that octant 6. If I let y become negative with that, I call that octant 7. Let x become positive, I like to call that octant 8. So we rotated through all 8 octants. It does take a little bit to grasp where those are, so play with the graphing applet that I've embedded in Canvas and let me know if you have questions with that. We just talked about 8 different spaces that exist in this 3D coordinate system. And if I'm calling them 8 separate spaces, then I need to talk about what separates them. The things that separate our octants are called the coordinate planes. Our coordinate planes are planes that are made up of all the points that exist with a fixed number in their ordered triple. For example, if I force x to stay at 0, but I allow y and z to move around, you can see that this point is moving almost freely, but it's stuck within a flat space. So this point is not really moving in 3 dimensions, it's only moving in 2. This point's allowed to move in the x direction, it's also allowed to move in the y direction, but it's not moving in the x direction. I hope I said that right. It's moving in the z and the y, but not the x direction. That means it's stuck in this plane. Any point that lives in the plane that you see on the screen has an x value of 0, but the y value and the z value can be any number you dream of. So the plane that you see on the screen is made up of all points where the x-coordinate is 0. This is called the YZ coordinate plane. Notice that the y-axis and the z-axis are inside of this plane, and the x-axis is poking straight through it. We can repeat this same idea, but this time let's let x change, and let's let y change. But let's keep z fixed. This time the point is allowed to move freely in the x direction, it's allowed to move freely in the y direction, but it's not allowed to move in the z direction. We would say then that this point is stuck in the z equals 0 plane, or the xy plane. All the points that make up the plane that you see on the screen have a z value of 0. The x and the y values can be whatever you want. We have one more scenario to come up with our coordinate plane, and that's where we allow the y value to be fixed. So we're going to keep b at 0. We'll let x and z change freely. And this time we see that the point is moving both in the x direction and the z direction, but it's not allowed to move in the y direction. It's stuck. We would say that point is stuck in the y equals 0 plane, also called the xz plane, because both the x and the z axis are within this plane. And if we're not 100% convinced that we're moving within that plane, we can rotate our screen and see that point is not moving outside of this plane. So here we have our 3 coordinate planes. If I move them all back to zeros, I'm also going to coordinate the colors of each of these planes so that we can help distinguish which plane is which. The plane x equals 0 is identified as the plane with the x-axis pointing straight through it. It's parallel to both the y and the z-axis. I made it red to remind us that the red axis, the x-axis, is the one that's spearing through the plane, where the other 2 axes are parallel to the plane. This is our x equals 0 plane, also the YZ plane. That's the coordinate plane. If, however, we allow x to change values, this plane can shift away from the coordinate plane and become a plane parallel to that coordinate plane. So positive is going to bring it forward, negative is going to bring it backwards. Similarly, we have the y equals 0 coordinate plane. This plane I made green because the y-axis is green and it pokes right through the middle of that plane. And if we allow y to increase to a positive number, that plane is going to move along the positive y-axis. Let's change our view so we can see that better. Or if I let y be negative, this plane is in the negative range of y, but it's still parallel to the xz coordinate plane. We have one more plane to talk about, and that's the z equals 0, or the xy coordinate plane. This is the plane that's that's flat on the bottom, or right in the middle. It cuts 3 space right in half. And if I allow that z value to increase, then it's going to lift up above the x and y axes. And if I allow z to go negative, it would go below the x and y axes. So if I have a z equals negative 3.5 plane, it is parallel to the xy coordinate plane, but it's below the xy coordinate plane. So we have our 3 planes here. I have our 3 coordinate planes showing on the screen. The red plane is the YZ plane, the green plane is the XZ plane, and the blue plane is the XY plane. Those 3 planes separate our 3 space into 8 separate sections. And I want to show you the point moving through these octants once again. So we have the white point at the origin right now. If I let x become positive and y become positive and z become positive, then I fit inside of that first octant where all 3 axes are pointing in the positive direction. But if I allow my x to become negative, then I shift into a different space. I passed through the red plane. And if I let the y also become negative, then I pass through that green plane into another space. So I'm now in octant 3. And then if I let x become positive again, pass through the red plane, and I'm in my 4th octant. So we just shifted around the top 4 octants where we let x be positive with y positive and z positive. Then we let x be negative, the other 2 positive. Then we let y become negative, and then we went back to make x positive. So we made an entire rotation on those top 4 octants. And we can do it again, but this time let's do it with z being negative, x, y are positive, and then we can rotate, make x negative, then let y become negative, and then let x go back to positive so that I can move through all 4 of these octants. Now that we've seen how to have a computer graph points for us, let's try some by hand. So I have a 3D coordinate system on the screen, and we're going to plot the point 1, -2, 3. So 1 in the x direction here, -2 in the y direction. Y positive is traveling this way, so y negative is going to go in reverse. So 1 unit and 2 units in the y direction would put us here. And then we're told to go up 3. Now on the z-axis, I don't have a grid, so I'm going to kind of rough it, maybe 1, 2, 3 units. To travel up, I'm going to do that same distance, but I'm going to do that right above my cross that I've drawn in the xy plane. So I'm about this high. That's where my point would be in 3D. Let's try another one. Oh, wait, before we do that, can we figure out which quadrant we are in? This would be, the positive top side would be, said quadrant, but I mean octant. Dang it. Now that we've seen how to graph in 3D using GeoGebra, let's practice doing some by hand. So I've got our 3 space axes on the screen. I'd like to plot the point 1, -2, 3. So I need to go 1 unit in the x direction. I need to go 2 units in -y, and that puts me right above this x. Lastly, I need to go vertically 3 units, and I'm going to estimate 3 units because I don't have a grid here. And a dashed line so that we know we're not drawing an arrow. And that would be our point. And if we want to figure out which octant we're in, let's remember that anything above the xy plane, that's octant 1, octant 2, octant 3, octant 4, And then if we were to travel below the xy plane, then we could talk about the other 4 octants. But since I know that I have a positive z, I know that I'm above the xy plane, and it appears that I'm within octant 3. Let's graph another point. How about -2, +3, -1? So we'll start at the origin. We'll move 2 units in the negative x direction. Then we're going to move 3 units in the positive y direction. I'm going to put an x in the xy plane there to say I need to be either above or below that. My z value is -1, so I need to go down in z about 1 unit. I am below the xy plane, so I know I'm not in octants 1, 2, 3, or 4. I know I'm below those. Below octant 1 is octant 5. Below octant 2 is octant 6. Below octant 3 is octant 7. And below octant 4 is octant 8. So our point appears to be in octant 6.